Okay, sounds good.
So anyway, again, I wanted to thank you, to take some time today to review some of these products that Buckley has to offer. I know it's a pretty crazy, challenging time for all of us, and we're all working outside of our regular routine. So I really appreciate the opportunity. Hopefully, sometime in the near future, Terry, as I mentioned, we can return to some sort of sense of normal practicing, and we can meet you guys in person, bring you some food, and make this a more casual experience. Anyway, so my name's Colin Dee. My title at Buckley is I'm a regional technical sales engineer. So I just recently joined the Buckley team at the beginning of the year, so back in January. So I probably haven't met any of you guys yet face to face, but I look forward to meeting you in the near future. Although I'm new to Buckley, I have close to 10 years in the industry. So I've worked for manufacturers such as Trane, Liebert, and most recently for Captive Air down in North Carolina. So I just moved up from Charlotte, North Carolina a couple months ago. While I was living in Ohio, as you can see at this little map I drew of my life story, I received a mechanical engineering degree from the University of Dayton. And since moving to New England, this pandemic occurred. So it's not the best time for me to move to a new city, but I haven't had a lot of time to explore and meet everybody. But I'm excited to be on the Buckley team and looking forward to working with all of you guys. Anyway, so I know that many of you have probably worked with Buckley and are familiar with our company. However, I wanted to make sure that you all have a good understanding of who we are and how we function before we start diving into some of these products. This year marks Buckley's 50th anniversary. We were founded back in 1970. So we have 6 different sales offices across New England, with our office headquarters and factory in Hanover, just south of Boston. So that's where we are based, and our headquarter office is down there in Hanover. Our branch offices are located in Portland, up in Maine, Manchester, New Hampshire, Albany, New York, and then Newington and Stratford, Connecticut. We have 2 of them down there. The Stratford branch kind of supports, the densely populated New York City, and our Newington office supports most of Connecticut, and then western central Massachusetts. Our factory at our main Hanover office manufactures general sheet metal work, so probably roof curbs, supports, flex duct, fire dampers, that kind of thing. Some louvers as well. All in all, Buckley represents just over 35 different product lines. So with our largest anchor product lines are Greenheck and Price. So you probably will contact us for that most often. But today we're going to focus on, of those 35 different manufacturers, we're just going to focus on 4. It shows Ebtron down here. Some of this is outside of our territories. Our Albany territory does not cover Ebtron, but today we're going to focus on Greenheck, Price, Antec Controls by Price. So this is a division of Price, and then TSI for the room pressure monitoring. As we dive through all these, we're going to try to relate this to how they relate to permanent isolation rooms, and then some of our temporary isolation rooms. So I think it's important to understand there are 2 different types of isolation rooms. So the first type is a protective environment isolation room, more commonly referred to as a clean room. So these are typically positively pressurized spaces which help protect patients with weakened immune systems. The second type, which we're pretty much going to be focused on today, are negatively pressurized airborne infectious isolation rooms. So the way that we have the presentation laid out today is, again, we're going to first talk about what a typical airborne infectious isolation room is, and what it looks like, and how we would design. So let's say we were going to design one of these rooms for a new location for a permanent application. We're going to look at what those products would be and how we would utilize those for those spaces. After that, we're going to review some of ASHRAE's newest guidelines, Terry, as we just talked about. So for due to the current pandemic, ASHRAE just released some new guidelines for the construction of these temporary facilities. And then we're going to finally talk about some other solutions that we at Buckley are seeing being utilized for these temporary facilities. So, first let's discuss I want to define what these rooms actually look like and how they're going to function. So here we have a typical layout for a standard isolation room. So for now, I want you to ignore all of the items that are pointed out on the image. So ignore all the stuff around the outside right now. Let's just look at how these things are constructed. I know this seems pretty basic, but I want to make sure that we all have an understanding of what we're going to be talking about today. So the entire system here is made up of two separate areas. So the first room being the ante room or the buffer room. So this room remains positively pressurized in relation to both the corridor and the patient room. The patient room, the bathroom included over here, remains negatively pressurized in relation to the ante room or the buffer room. So this ensures that the patient is isolated from the rest of the hospital, as well as the rest of the hospital is isolated from the patient. So depending on what devices we choose to control the space, we may need to utilize pressure sensors, which are shown right here and right here. You know, depending on whether we want to monitor or control via these pressure devices, they're still going to be required. We're going to talk a little bit about different, on the next slide here, different methods of controlling this space. But nonetheless, these pressure sensors are going to be required. Over on the top right side of the image, you can see our exhaust ductwork. So this is, we're either going to be pulling out, this can either be exhaust or return. This can go up to a lab exhaust fan or high plume fans, or these can be recirculated if we have the right type of filtration. Over on the left side here, we just have supply. So this is going to be here we see a valve and some reheat coils, but really what we're doing is pressurizing the space with the supply air over here. So really there are two methods of control, as I just kind of mentioned. So they're either going to be room pressure control or volumetric flow rate. So when we look at control variables inside of a space, we need to pay attention pretty much to 4 different variables. So those variables are volume, flow, pressure, and time. However, the most commonly used variables that we're going to look at here are the volume and the pressure. So the other two, even though they are still considered variables in these spaces, they're almost always associated with the other 2 variables. So let me kind of further explain. If you have a flow controller, your flow is set. Okay, so your airflow into the space is set, which directly affects the volume flowing into the room. Therefore, our flow control is directly associated with volume control. So on the other hand, the time controller, the time variable is typically associated with a pressure controller. So what does all that mean? I mean, let's say somebody opens a door leading into the space. You know, what is immediately going to change in this space? The pressure of the space. So if we were operating based on pressure, a signal is going to be sent to an air control valve. We're going to wait a certain amount of time for the pressure to either build up or drop down to meet a certain pressure set point. So what did that take? Time. So this variable is dependent on many things. You know, how large is the room? Do we have a tightly constructed room? You know, what is our air leakage rate in the space? How long was the door open? You can even say, how fast did it take to meet the pressure set point? Did we overshoot or undershoot that set point? There are a lot of questions to be answered. That's if we're driving on room pressure. So on the other hand, if we chose to utilize control via volumetric flow rate, we only need to pay attention to how much air is going into the space and how much air is leaving the space. There's no longer a time variable. So no matter what is going on in the room, whether doors are open or closed, we're constantly assured that the pressure, so our air changes in that space are going to be correct. So how we control our air control devices and what type of air control devices we're going to have is the first question we need to ask. And the preferred method of control in these isolation rooms is always going to be volumetric flow rate. It simplifies everything, and it takes some of the variables out of play. So as I said earlier, that doesn't mean that pressure sensors are not going to be required. That just means we're going to use them to verify that the system is functioning properly, to maintain safe working conditions for the patient, the nurses, and the doctors, so everybody in the facility. So what types of control terminals or air control devices should we use for these isolation rooms would be the next question that we need to ask ourselves. And this is where Antec Controls comes into play. So Antec Controls, as I said earlier, is actually a division of Price. These valves used to be branded Price Critical Controls. So if any of you are familiar with that name, that's where you probably recognize that is part of Price. But that Price Critical Controls brand has since been changed into its own product line. So, and that is Antec Controls. So Price has been manufacturing air control terminals and valves for a long period of time, even though the Antec brand may be new for some of you. So before we dive into the nitty gritty of control valves, I want to start with the basics. Again, this is easier to lay out. I like putting out drawings and stuff. So when we get to do this face to face, it'll be a little bit more powerful. But for now, I want to start with the basics so we have a good understanding of this. So I think it's important to understand some of the main differences between the three types of terminals that we're going to talk about today. So those three types of terminals are air terminal units, so better known as just a standard VAV box, high accuracy terminals, and then Venturi valves, so a true Venturi valve. Both VAV boxes and high accuracy terminals are very similar in their operation, as they both share closed loop controls and they are both pressure dependent. Venturi valves, on the other hand, operate entirely different. So they have an open control loop and are pressure independent. We're going to define exactly what those two terms mean, but just remember that Venturi valves live in their own world. They operate totally differently than a standard VAV box or a high accuracy terminal. And Venturi valves have many advantages that standard VAV boxes and those high accuracy terminals do not. So in a pressure dependent system, which is what we're going to look at over here on the left side of the screen, the airflow through the valve going through, these are just dampers here, is dependent on the pressure in the ductwork. So we have three VAV boxes here, or let's say they're dampers, all allowing 700 CFM through a piece. So if the airflow requirement to this middle space here, let's say it's reduced to 200 CFM, what's going to happen to the pressure in the ductwork? It's going to increase, okay? Therefore, if we don't adjust the other dampers, the flow through those dampers is going to increase. So if we just go ahead and block off this damper, what's going to happen is the flow is going to increase in both of these valves. In a pressure independent system, which is what we see with Venturi valves, the system has the ability to deliver a specific airflow independent of that pressure in the ductwork. So let's pose the exact same scenario that we just looked at on the left, where this middle damper only requires 200 CFM instead of the 700 CFM. Okay, so the other two dampers here are going to maintain their same airflow. So even though we blocked this off and reduced it to 700, the flow in both the top and the bottom valves here didn't change. So how does this happen? So here's a look at both of these devices. So when we talk about closed loops and open control loops, I think it's important to understand the differences between the two. So with a closed control loop, there is always a direct link between the controlled variable. So for this application, it would be airflow, and the controller. So what happens in a VAV box or any controlled loop system is that there is airflow through the box that is measured via some sort of sensor, pressure sensor, or transducer. So this sensor sends a signal to the controller that controls a damper that then reacts and varies the airflow. Okay, so then the sensor again measures the airflow, sends a signal to the controller. The controller then moves the damper, and we have you see how we have this signal here where we have a closed control loop, and it goes on and on and on. Okay, a lot of times we call this a feedback loop. We're always going to measure this flow and then correct the flow. There's on the right side, on the other hand, in an open loop, what ends up happening is we have no feedback. There is no measurement device. So in here where we were actually measuring the airflow or measuring the pressure, then calculating airflow, sending it to a controller, we're not doing that in a true Venturi valve. The airflow is strictly based on the position of this cone and spring inside a valve, okay? So it operates independently of the pressure in the ductwork. It will react to the pressure, but the airflow is strictly based on a position of this cone. So once again, looking back at a standard VAV box, so again, closed loop controls and a pressure dependent system, airflow is measured and a signal is going to be sent to a controller that moves the blade damper that adjusts the airflow. The loop, this closed loop, can often lead to slower response times as the system has to go ahead and balance itself out. Also, these units require some sort of straight ductwork leading into the unit and exiting the unit to encourage laminar airflow. The reason for this is to ensure that the airflow velocity measurement that is being taken is accurate. Without laminar flow through this device, we're going to have an inaccurate measurement and the device is not going to be able to function as designed. So, however, no matter how accurate the device is, there's an inherent problem at low airflows through this device. Okay, so we have a butterfly damper, and when this damper is very close to being fully closed, so the at low airflow being allowed through the device, all of our accuracy is lost. Okay, so if it's just sneaking through, we have very low control over how much air we're allowing through this device. So these devices, so a VAV box is great for a temperature control application. But if precise airflow delivery is required, like we do in isolation rooms for all healthcare applications, this is probably not the device we're going to want to install specifically for that application. So the second type of air control device we're talking about is a high accuracy terminal. So this functions very similar to a standard VAV box. It uses the exact same closed loop controls, and it remains, again, a pressure dependent system. However, the device can more accurately measure the airflow due to the Venturi body. Okay, so the only thing that changed here is instead of using the same diameter ductwork running through this entire valve, now we're using a Venturi body. So a Venturi body generates a pressure drop as air passes through this device. So what we're doing now is measuring the pressure drop with two separate probes, which you can see right here and right here. When we measure that pressure drop, our accuracy of the pressure measurement increases, which again can be calculated directly to an airflow. Okay, so however, again, due to its inherent blade damper operation, just like the VAV box, we're still going to see that low end inaccuracy as the blade damper is very close to being fully closed. So this is a better solution than a VAV box, and it remains more economical than a Venturi valve. But if we require a fast responding and accurate airflow management device, we really, really need to look at a true Venturi valve. So again, let's take one last quick look at a true Venturi valve. So here we have a Venturi body with a spring and cone assembly internal to the unit. Okay, so airflow again in this device is not measured in any way. So this device is calibrated out of the factory, and at a specific position of this control arm and the cone in this body, it is designed to allow airflow through the device between two pressure ranges. We have two different types of pressure ranges. We'll work with you when we're designing these systems to determine what valve is best. We just need to know an operating range of pressure that's going to go through this valve, and then we can design the valve perfectly to operate at certain airflows. Now, the nice thing about this is we don't have that low end inaccuracy. So as this valve fully closes and it gets further down into this body and reduces the airflow, we're still going to have stable opening. Okay, so we don't lose that inaccuracy as we approach the minimum airflow allowed through this valve. So on the left side of the slide here, we see a valve in a 1-inch static pressure. So this is a relatively low static pressure condition where the spring inside the cone is not compressed very much. Here's a little cut so you can see the spring operating in this. This allows for more space and more airflow to move through the valve. So you can see these orifices on top. As this cone is further towards the inlet of this valve, there's more space around the cone for air to flow. Okay, on the right side here, we see the same valve in a higher 3-inch static condition. So this is where the spring is now compressed due to more pressure at the inlet of this valve. The orifice size here is reduced. However, due to the increased pressure, we're still allowing a constant flow through this valve. So even though I don't have a specific CFM, let's say we're allowing 500 CFM through this device here on the left side, this is the exact same. So we're looking at 500 CFM coming out here on the right side as well, even though we had pressure change. Okay. Now, in a variable air volume system, we can go ahead and send a signal to an actuator that moves this control arm. Otherwise, in this condition, the valve is just going to function as a constant volume valve that we can manually adjust in the field. Okay. Does anybody have any questions on that? All right, so that pretty much sums up our discussion on air control valves. And we're going to move on to the exhaust side of things here. So probably all recognize the Greenheck brand. Greenheck offers a wide variety of products, including dampers, supply fans, energy recovery systems. We can even go into kitchen ventilation systems, DOAS units. But today we're just going to focus on their high plume laboratory exhaust fans. So what differs a general exhaust fan from a laboratory exhaust system? Why would we need to use a lab exhaust fan instead of a standard upblast or downblast fan? The problem here is that in these systems, we're typically exhausting air that is highly contaminated by either hazardous gases that need to be diluted or air coming from hazardous areas such as pharmacies, or today, like we're talking, isolation rooms. So when we're selecting these systems, we really have four main objectives we need to pay attention to. And those are: one, removing hazardous or noxious fumes from a lab. Two, we need to dilute those fumes that we're exhausting as much as possible. Three, we need to expel the fumes away from the building so they do not recontaminate any of the roof area. And then 3 and 4 are kind of similar. We need to prevent any makeup air units from pulling that exhaust air back into the building. So there are two real main code requirements that apply to installing a lab exhaust fan. The first one is that the minimum stack discharge velocity needs to be 3,000 feet per minute. Some people now are seeing this, and code is changing over time as it always evolves. This number is actually going to be going away shortly. And even though the number is going to be taken out of code, it still doesn't mean we shouldn't pay attention to it. It's still a good guideline for what our discharge velocity should be right at the end, at the discharge of these fans. And the second code requirement we really need to pay attention to is that the stack height needs to be 10 feet minimum above the roof line. So where this guy's standing here, 10 feet minimum from here to the top of this exhaust fan. Now, remember, these are just minimum requirements. So many times an application may require for other types of design considerations. So for example, are there taller buildings going to be, around this space? What is the average wind velocity at the location of this fan? So the climate can change things. So we need to take all these things into account and really maximize this plume rise. So not to get too in depth here, as there are a wide variety of people on this call. And I don't want to turn this into a math class for anybody, but calculating plume rise is critical before we install one of these fans, before we ship this out to a final location installation. There are many variables that play into this entire design, including the airflow, the discharge velocity, the actual nozzle diameter of the fan. Some of these fans can come with a variable nozzle, so we can continuously maintain a maximum plume rise and in even a constant discharge velocity here. And we'll talk about that a little bit more on the next few slides. But nonetheless, that variable nozzle is an option. But we need to pay attention to all of these variables. And there are many different ways we can calculate this. And internally here at Buckley, we have the ability to do these equations. And we have systems that will properly design these fans. So one of the really cool items that we have available when selecting and designing these fans is our plume concentration modeling tool. So we can input here a specific fan and all of its design parameters that we just talked about and simulate actual specific concentrations at certain heights and certain distances away from the fan. So this ensures that no matter the application, we can pretty accurately determine how the fan is going to perform, even with variable conditions, such as airflow, wind speed, and even different chemical concentrations. So we can put an exact, type of chemical in here and look exactly how it's going to perform in a specific location. Now we use this tool pretty frequently to ensure that the fan that we are designing is going to operate exactly as it is in the field. Before we had this tool, there were definitely projects where we were installing these fans, and then we took into account all these parameters and we thought it was going to behave properly, but you know in reality, the fan may not have performed up to its design parameters. So here we actually have the ability to simulate it before one of these gets right into the field. So here's some quick information on our most commonly used laboratory exhaust fan. This is the Greenheck Vector H. This fan is designed for anywhere between 500 and 26,000 CFM, and really between 0 and 4 inches of static pressure. So really up to 4 inches of static on this guy. So up to 3 of these fans can be paired together into a single system. So we can put them all onto one box. So what I mean to say is all these fans can be installed on a common exhaust plenum or a box for additional capacity, or if you need some redundancy. So the fan that you see here on the left is our standard version of this fan. This is an exhaust only configuration. However, these fans do have the option to add this bypass to maintain constant speed and assist with dilution of air as these hazardous chemicals are exhausted. So the nice thing about this specific Vector H, and probably why we see it used the most, is it's quick and easy install. So basically all you have to do is drop this fan on the roof. It's got a single penetration that's required, and run power to it, and you're good to go. This is probably the most common fan we're seeing used for these isolation room applications. And although this slide again doesn't show them, there are several different nozzle configurations, including variable geometry, dilution, and sound attenuators for all of these nozzles. Any questions on this fan specifically? So due to the nature and application of many of these laboratory fans, downtime's not really an option. These are critical facilities, so we need to build in some sort of redundancy. And there are really 2 types of redundancy that are frequently used in all of these applications. And the first type that we see here is going to be N+1 redundancy. So this means that the system is going to be designed so that any one fan can go down for maintenance, or whether the thing crashes and breaks, the remaining fans are going to be able to handle the load. So what we have on this slide demonstrated is a 12,000 CFM exhaust system, where the one exhaust fan is in standby, and then the other 2 fans are running at their design capacity of 6,000 CFM. They're basically splitting the load. And then naturally, based on different sequence of operations, we can work this out with you specifically. These fans can be rotated via scheduling to ensure equal runtime. On the other hand, there is a second type of system, so that would be N-1. So here we have the exact same 12,000 CFM exhaust system. However, all 3 of the fans are going to be running at the exact same time at some sort of partial load. So let's say they were all running at 4,000, 4,000, and 4,000. If one of these fans goes down or is shut down for maintenance, the other 2 fans are going to be designed to be able to ramp up and then carry the full load and split 6,000 CFM apiece. Okay, the benefits that the reason we're starting to see N-1 quite a bit is, these fans are always going to be running at constant speed and lower speeds. So this means a lower nozzle velocity, quieter operation, less power, and equal runtime for all the fans. So there are benefits to both of these redundant scenarios, both N-1 and N+1. However, it's really usually up to the owners is how they want to operate or which scenario they prefer. So the Vector fan line is definitely the most optimal solution. That is the best solution for any isolation room application. However, if certain constraints, say, roof space or budgetary limitations, or even time doesn't allow for the full installation of a Vector fan, Greenheck also offers this fume jet line. So it's not as robust as the Vector line, but pretty much we've seen it function as a viable alternative to those Vector fans. So these fan capacities vary anywhere between 500 and 15,000 CFM, and up to 8 inches of static pressure. The reason they can handle a little bit more static is these are basically a beefed up utility set fan. Okay, they basically are exactly, it's a utility set fan with an extended stack on top. Okay, so what we can do on top of these stacks, we have different options here. I know I talked about some variable nozzles. We don't have that on this specific line, but we do have a manually adjustable nozzle. So if we're not getting the plume height high enough, we can go ahead and manually adjust this nozzle to increase the nozzle velocity in the field. Otherwise, we can also add a fixed nozzle just to increase some plume height at the discharge of these fans. These are on a little bit quicker lead time than our vector fans, so if you need something quick, this is probably the route we're going to go. Nonetheless, if we're designing a permanent lab solution or permanent isolation room solution, we're definitely always going to recommend the vector line first. Okay, so far we've only been discussing, products that we would typically utilize for the construction of a brand new isolation room. So I kind of want to shift the discussion now to directly relate to temporary isolation rooms that are being constructed due to the current pandemic. So here's a cartoon that I found, and not to make light of the current situation that we find ourselves in, but our hospitals and healthcare systems find themselves in this exact scenario. Okay, so they're currently dealing with a highly contagious and infectious virus without the proper facilities to function and treat any sick patients. So due to the lack of these proper facilities, both the patients and the doctors, pretty much everybody in the hospital, are now all at a higher risk. And these types of facilities that are required in times like this are difficult to find, and many spaces are being converted rapidly into temporary isolation rooms. We've seen dormitories, we've seen larger, the convention center in downtown Boston starting to be converted over to assist with this kind of stuff. And the products that we're going to cover from here on out can definitely be used for the construction of permanent facilities. However, I want to focus on their applications as they relate directly to the surge of temporary spaces that we're seeing today. So ASHRAE recently put out a full presentation, this is about a week and a half ago now, updating the community with some guidelines and recommendations for the new construction of temporary isolation rooms. And their main message here in these guidelines was keep it simple, okay? It's going to be extremely difficult right now to construct facilities that are going to operate perfectly, but rather we're going to have to, make do and proceed with the best options that we have available. So we don't want to waste any time or mental energy or money designing these temporary facilities. All we want to do at this point is save lives, okay? So if we are tasked with designing or retrofitting a temporary emergency isolation facility, the first thing that we need to do is establish some minimum standards, okay? ASHRAE in this presentation, basically, they understand that we're not going to be able to construct these facilities entirely up to code. What we need to do is define rooms and areas that are available, make a plan, and get to work constructing them. One other item that they mentioned was to ensure that all the hospitals are aware of 3 basic clinical modes that they can operate under. And right now, most of these facilities are in some sort of small or large scale surge capacity mode. This allows many facilities to take exceptions to certain codes to handle this large inrush of these patients. And it's important to note that these temporary isolation rooms are not true airborne infectious isolation rooms, but they're rather facilities that are being utilized to keep everybody as safe as physically possible and prevent the spread of this virus. So in this presentation, they laid out 6 different options for these temporary isolation rooms outside of their true design conditions, okay? So these options are drawn out on the right side of this slide here. If you take a quick look. So option 1 on top, it shows a room with access to a nearby window here. So what they're utilizing and recommending is a fan filter unit with HEPA filtration. So a HEPA filter thrown in this fan filter unit, and it's going to be used to exhaust air directly out of a sealed window. Now it's important to note in this scenario that all returns in the space basically need to be blocked off to ensure that the room is going to be negative, because the air is going to come from somewhere. And if we block this off, that's the only way we're going to maintain proper filtration and negative pressurization in the room. Now, option 2 here that they laid out is very similar to option 1. They're still recommending this solution over the rest of them without HEPA filtration. Obviously, we want to HEPA filter this virus, but it's more important to get it out of the space and maintain negative pressurization than anything else. Option 3 here, what we're looking at is a fan filter unit again with HEPA filtration being ducted into the return or exhaust of some space. Okay, so this is difficult in some spaces. It's obviously or usually requires some existing exhaust or return system. This scenario should really only be used if ducting to the exterior is not a viable option. And then the other thing that always comes up when we're talking about this is if this is a variable air volume system, we're basically going to open another Pandora's box of problems as pressurization is going to become infinitely more difficult. So try to avoid this, but again, this is where ASHRAE is ranking this option in a temporary facility. Option 4 here shows another HEPA filtered air being pulled out via this fan filter unit and being ducted into the corridor facility. Now, again, we'd rather get the stuff outside the building, but if the only way that we can keep this patient safe and build this isolation room is by HEPA filtering this air and then pulling it out, this is again another viable solution that ASHRAE is presenting. Now, option 5 here doesn't allow for any isolation and pretty much should be the last case scenario where some filtration is going to be utilized and just to help prevent the buildup of the virus in the air. This is probably the last case scenario. The last option though here, number 6, they presented is basically utilizing some sort of protective portable isolation tents. So we're seeing these tents being used in those larger open facilities to create individual isolated areas for these patients. In this case, the air is going to be pulled out of this tent, HEPA filtered, and then exhausted either out of the building or into the return of an existing room. These are, again, we've seen a couple. There are obviously more options than this. These are the specific 6 options that ASHRAE presented in the last 2 weeks. I know that everybody's facilities are a little bit different and everything's unique here. I just think the important thing to note here is we need to look at these facilities and come up with the best solution as quickly as possible. Because again, we're just these aren't going to be perfect and they're not going to be true airborne infectious isolation rooms. But for these temporary facilities, we just want to create as many negative spaces as possible and do our best to keep everybody safe. So Buckley Associates, we are New England's representative for all price products. So the price critical environments team right now is focused on providing a lot of fan filter units in multiple configurations for all of these options that ASHRAE presented. And these are being provided on standard 2 to 3 week lead times, but there are quick ship options available for specific COVID-19 related projects. So talk to us if you got a really quick project and it's moving rapidly, give us a call and we'll try to pull some strings and get these units to you as fast as possible. So in general, a fan filter unit, you've probably seen these before, it's just a powered filtration box. So it's primarily used in the healthcare industry. Due to typical healthcare applications where we're going to be using these, they almost always come with some sort of HEPA filtration. They have the ability to come with some other filters, but right now I'm going to focus specifically on HEPA filtration. These can be configured in both supply or exhaust applications. They come in standard sizes of 24 by 24, 24 by 36, or 24 by 48, and they're designed in those sizes so they get dropped right into a drop ceiling application. However, these can be utilized in many other configurations, as we're going to see on the following slides here. Each one of these fan filter units can be either stainless steel or aluminum. So they have the option to be either room side or bench side replaceable as well. So a lot of these facilities don't want to be able to don't want to have to pull the full fan filter unit out of the ceiling to replace a filter. We can leave it in the ceiling, basically hinge it down, pull the filter out, and throw it back in for quick install. One of the most recent updates, I don't know if you all have seen this before, but Price has added a little optional LED indicator in one of these, so anybody can really see in the room whether it's time to replace the filter without having to regularly check the filter, cleanliness. HEPA filtration can be verified, so there's a built-in aerosol port in here. So at commissioning, we can verify that we have proper HEPA filtration via that aerosol port. It's easy access, it flips down, and it's built into every one of these. Let's talk the next couple slides here about the different configurations we can use these in. On this slide, I just wanted to show this. It's kind of hard to see, but you can see there's a little green LED indicator here. That's what I was talking about, where it shows that this filter unit is in proper operation. And then to maintain sealed, proper sealage around the filter to maintain proper filtration, we have a little gel seal. So when this drops in, no air is going to sneak around this filter. So each one of these units, like I said, comes in different configurations. This is how you're pretty much going to see it all of the time. The ceiling mounted exhaust fan filter is probably what's going to be used in a more permanent application. So whether or not we're talking about new builds or temporary builds, this is where you're going to see it. So the fan filter unit is simply installed in the ceiling above the patient, where the air is pulled directly up, filtered, and then either thrown into exhaust or return air ductwork. So an exhaust fan flow filter unit, it can also be placed on the floor of a patient's room. So we have the ability to go ahead and do this and then just duct it into an exterior room. Here we can see it's being ducted pretty to the outside of a building. It's important again in this scenario that we have to seal all cracks in here to ensure proper filtration and negative isolation of this room. But nonetheless, this is another configuration that we are seeing quite a bit for these temporary facilities. And then lastly, the last configuration here, we see a standard supply air FFU, and it can be placed right into the door of one of these facilities. So we've already started to see this application in a lot of hotel rooms that are being converted. So what they're doing is taking this fan filter unit, putting it right into the doorway, sealing off the other cracks, and then HEPA filtering and exhausting that air into some other space. So this is the easiest conversion we've seen for either dorms or hospitals. This is the unit that they've been using for those specific applications. Any questions on those recommended applications, the ASHRAE options that they've presented? Nothing really? All right, let's move on. So before we wrap up, I have a little bit of more information regarding some of the pressure monitors we're seeing used. So TSI is one of the most well-known manufacturers of pressure monitoring. They have a wide range of products, and today we're just going to focus specifically on some of the pressure monitors we're seeing used for temporary ISO rooms in today's pandemic. So really quick, the way that TSI measures their pressure is via a thermal anemometer. So I'm sure many of you are familiar with this technology, but for those of you who aren't, basically what happens is there's a sensor that generates a certain amount of heat, and it does its best to maintain that temperature inside a tube. But as air passes over that sensor, it's going to carry away some of the heat in a certain direction. So the amount of energy that it takes for that sensor to maintain a certain temperature is then equated to an airflow through the tube, and the direction of that airflow is determined by a second sensor that can either sense the lost heat or doesn't sense lost heat. So now we're going to determine which way the air is going. So with both of these inputs, the sensor is then able to determine the pressure in relation to an adjacent room. So ASHRAE 170 requires that every isolation room has a permanently installed visual device or mechanism to constantly monitor the air pressure differential in a room. So while the permanent device can be as simple as a flutter strip or a calibrated ball and tube, the most reliable way to measure and monitor room pressure is going to be with the use of an electronic pressure monitor. This is really the only way to do it. So when properly installed, the monitor is going to be able to continuously provide confirmation and a variety of points, including pressure, temperature, and humidity in all these spaces. So even in temporary rooms, ASHRAE is still requiring some sort of pressure monitoring to allow all of the healthcare workers to know the status of the area that they're working in to ensure that it's still safe. So here are some of the most common pressure monitors we're being seen installed on a daily basis. The NSD8 is the nurse's station monitor, and this can be connected up to 8 rooms. It's typically installed so that all nearby rooms can be measured or monitored from one single location, okay? The RPC30 shown in the middle here can both monitor and control one single room. I didn't really touch on it on this presentation. I know we talked about different types of pressure control a little bit, and we always usually want to go with volumetric flow, but this device can be used both to monitor and control the pressure in a space. So depending on what current setup you have or how we want to control those air control devices we're talking about, we probably want to use an RPC model. And then lastly, the RPM 20 specifically here monitors both temperature and humidity for up to 3 rooms. We do have the RPM 10 available as well for 1 room. Again, monitoring only. We actually have a couple of these RPM 10s in stock here in our Hanover office. So if you need something quick, let us know. There are some quick quick ship options for these as well. So reach out to us whenever you get a chance if you see a quick requirement for these. Again, TSI is taking a lot of exceptions to their standard lead times for the COVID related projects. So call us as soon as you have an application.
Hey, Colin, Tim Elliott, that RPM 20, if you could go back one screen.
Yep.
How much tubing can you put on that? Is there a limitation to, obviously you locate this in a central room, like an ante room or something, and then you're looking at pressures in maybe 3 different rooms. You can run tubing to those 3 different rooms, obviously, right?
So typically what we see for those is there's tubing run between the two rooms. I don't know if there's a specific, off the top of my head, a length requirement. I know it's probably in our specifications. I'll get right back to you after this presentation.
Yeah, could you? Because I spec'd one of these out for a project that we're getting ready to look at submittal, and we put 2 of these in because we had 6 rooms, and I'm assuming that we can, route the tubing. I'm not talking maybe 15, 20 feet tops. Yeah.
Okay, cool. Yeah, great question. Let me look into this. As soon as I get done with this, the next few slides here, I'll shoot you an email with the specific specifications, see how far we can run these tubes.
Okay, thanks.
Yep. So really quick, we would always prefer to use the standard TSI robust products on that past slide. But we started seeing this specific device used for standalone rooms only for COVID applications. So we typically use this device for commissioning. So somebody will throw this in his truck and use it. However, it's on a 2-day lead time. We can sync this. It's got Bluetooth. It's built in. We can sync it right with a mobile app. It's a great resource for quick temporary setups. So again, if you come across a scenario where you need to use one of these quick, we can assist and provide these. Probably wouldn't recommend this ever for a permanent application, but for the applications we're seeing in the last 2 weeks, this thing's being used quite a bit. The other room pressure monitoring, I'm switching back to Antec here just for a quick second. They're providing this on a 2-day lead time for any orders of 50 and less. So again, they have some more robust monitoring devices that we would usually recommend over this one. However, it does have every capability to monitor pressure in these temporary rooms. The really nice feature and the feedback we've gotten on this is this LED sidebar. So this green sidebar here is actually an LED strip, which changes between green and red depending on the pressure reading. And then there's also an audible alarm built right into this. So again, 2-day lead time for orders of 50 and less on these guys. So we've been seeing this thing utilized quite a bit. And then lastly, Buckley recently teamed up with this company in Minnesota called Ducts and Cleats, who have recently started producing this device called the ISO Air system. This is really a true plug-and-play solution. Only 120 single phase, plugs right into the wall, can be floor mounted, go right into a door for door mounting or window mounting. So it's available in all those configurations. This unit can handle up to 1,000 CFM. It's got an EC motor built right into it. Ships on a 7 to 10 day lead time. We've already seen this specific unit being utilized in some of the hospitals down in New York City to maintain negatively pressurized and filtered spaces. So another great solution that Buckley has to offer. If you have questions on this, we can get you specifications. Newer product. So if you got questions on this, reach out anytime. These are in super high demand. So if you need a few, let us know ASAP so we can reserve a spot in the Ducts and Cleats production. And that's really all I have prepared today. So I know that all of our lives are kind of turned upside down right now. So I wanted to thank you all for the time. I know we're still getting used to all this quarantine life that we're living and working from home, but I can promise you that Buckley is still working hard and we're staying as busy as ever. So if you have any questions, let me know. I know Tim, I'll get back to you on these pressure monitors and some guidelines on those. Does anybody have any questions on the ASHRAE recommended options? If anybody has any questions, feel free to reach out. Otherwise, thank you for the time today. I know these temporary isolation rooms are going up quick and they're kind of just being thrown up. So let's do our best to stay safe and design these rooms as quickly as possible and keep our hospitals safe.
Okay, thanks,
you.
Colin.